Okay, great. Thank you, Joseph. So your endemic is a disease that's always present in the population. Common cold is really kind of the best example of that. Then we have our epidemics, and in epidemics, so this COVID-19 started as an epidemic in Wuhan, China, and it had slowly started to spread out. And once it reaches a certain number of countries and other parts of the world, it's then considered a worldwide epidemic. The last pandemic I can truly think of, SARS was almost classified as a pandemic. They're calling it a pandemic now, but at the time they did not. It was still considered an epidemic. So it was never, the World Health Organization never really officially called it a pandemic. HIV is the last officially determined pandemic that I can remember. There may have been one I might be forgetting about, but HIV was a big one back in the late 80s, early 90s. So that brings us to the concept of herd immunity, and this also plays into this whole pandemic that we're in right now. So we've talked about herd immunity in the past. Herd immunity occurs when a high enough concentration of a population has immunity to a disease. So this whole idea of flattening the curve, that kind of thing, it's interesting. I heard an interview last night with one of the guys from Johns Hopkins Bloomberg Public Health College, and they were talking about the antibody tests that are coming out. Now, you guys know that we produce antibodies once we've been exposed. So the importance of these antibody tests that are supposed to be coming out soon is that we can determine who has actually had COVID-19 and if they have some immunity to it. So if you have a high titer, they might be titers, they might be lateral flow devices or ELISAs, but regardless, if we have antibodies, this means that we have been exposed to the disease, we have either had it or gotten over it or had exposure and we were asymptomatic. Regardless, it will be assumed that we have some kind of immunity to the COVID-19 virus. This means that those people who have immunity to it can now begin returning to work. And the importance of that is now our economic factor. So people who have antibodies and have resistance to the disease can now go back to work and start running businesses again, start running stores and offices, and kind of getting our economy back up and running, get our economy back up and running so that we can hopefully start coming back to normal. As far as getting it again, Wanda, there is still research on that. So they're not sure. I mean, think about it. This virus has really only been around, the virus has only been around for a few months that we know of in the human population. So we have no idea right now if they can be reinfected with it. The idea right now, the theory right now is that no, they cannot. I will say I went back and did some research on SARS, because this virus is very, very closely related to SARS. And I wanted to take a look at what they did with the SARS virus in terms of treatment and in terms of length of immunity. And one of the things they found with SARS, and this is why we don't have a vaccine against it, is that the glycoprotein spikes that are found on the viral envelope, yeah, I don't know if it's true or not either, Wanda, because we just don't, the virus hasn't been around long enough for us to figure that out. But those viral spikes, they instill immunity, but apparently it's somewhat weak. And when they tried to recreate that infection in a vaccine type of environment, they did this in what's called engineered tissue. They were using tissue cultures to experiment with this vaccine. And what they found was the efficiency of the vaccine was very short-lived. It was about 18 months. And what that means was if they were to use that vaccine, you would really only have immunity for about a year to 18 months. After that, you would need to get a booster. That's very short-term immunity. That might be great for, say, healthcare workers. We could vaccinate healthcare workers, and so over the next year, we can ensure that our healthcare workers have some immunity and they're able to stay in the field. They don't get sick and have to leave, and then we're low on healthcare workers. So that would be the first population that would be targeted, even with a vaccine that may be short term. But the problem with that is that after a year or 18 months, everybody's got to get revaccinated, or we're kind of right back where we started. So SARS was not a very good candidate for long-term immunity. And what they're trying to determine now with COVID and with SARS is there reinfection immunity? Are we able to, do we produce enough antibodies and memory cells in our immune system to ensure that we have some kind of longer term immunity? If we do not, then what we have is a loss of herd immunity. We have to try and coordinate the vaccine schedule. Imagine trying to coordinate everybody in the world to get vaccines around the same time so that we could stagger this immunity and ensure that the multitude of people, the majority of people, are vaccinated on a regular basis against this virus. So that herd immunity becomes really important. Desreen.
Hello.
Hello.
Hi,
What can
how
I
are
do for
you?
you?
Hello,
I'm good.
everybody. It's I don't want to seem like I'm spreading conspiracies, but
Uh-huh.
there's so many different ways to look at this COVID-19 pandemic and how it's affecting the
Mm-hmm.
world and really how the government's dealing with it.
Mm-hmm.
This herd immunity, I just have a question basis. Was it something that was created in the modern world, or did herd immunity exist, like, let's say, when there weren't necessarily vaccines and like population control, I mean, not population, well, germ control and all those type of things?
Well, in terms of theory of what herd immunity is, then yes, it would have existed before we had vaccines. What vaccines do is vaccines allow us to create herd immunity without getting sick. So these antibody tests that I was just talking about a few minutes ago, the idea behind that is that let's find out who is already exposed and who has immunity to it. And the greater the number of people with immunity, the more effective the concept of herd immunity becomes. So we want as many people to have antibodies against this disease. We want as many people to have some kind of defense against this disease as possible. And the greater the number of people with immunity to a disease, the more likely we are to prevent the spreading of it. This is also why naturally they're talking, right? They talk about these epidemiological curves, right? So they're talking about, this rate and how we want to flatten the curve. Part of the natural flattening of the curve, it's unsustainable for a disease in a population to just continue going up. And that would be unsustainable in an evolutionary sense and in a molecular sense for the virus itself. And that is simply because the virus would eventually kill everyone and run out of hosts. That's the theory. So what happens in these epidemiological curves, whether or not we quarantine and do what we're going to do, at some point in time, that curve is going to flatten. What we're trying to do is we want to flatten it down here, right? So this is our number of population. We want to flatten the curve at a low number. So we're trying to flatten that curve sooner or more quickly than it would normally do on its own. So if this is 1 million people with the disease, this virus may only flatten its own curve when it's at 100 million. And I don't want to flatten it at that number. That's an awful lot of people. I want to flatten it at 1 million. I want to do it much sooner. So the sooner I can flatten that curve and even come on the downside of it, the better off we're going to be population-wise. And so this is what they were looking at. I'll pull up some of the graphs from Hopkins. This is what they were looking at when they were comparing these transmission curves between countries. So this might be China. This is the US. What did China do that the US did not, that they were able to flatten their curve much sooner? Well, China quarantined more quickly. They put people under smallpox and the milkmaids, Jada, yes. China quarantined more quickly. They did the stay-at-home rule more quickly. China is also a communist country, so they could enforce those rules more heavily than we can here in the United States. Here in the US, we ignored the signs, so we allowed this virus to kind of develop on its own and transmit through the population on its own, unchecked. And it isn't until we got into high enough numbers that we were like, hey, wait a minute, we need to stay home, we need to not transmit this to each other, that sort of thing. Now, natural flattening of the curve, right, stopping this from going along, occurs two ways. One is herd immunity. People get the disease and recover from it. And when they recover from it, as long as they have reinfection immunity, then those people will no longer transmit the disease and they won't carry it. The second part of it is people who contract the disease and end up dying. So those people, once they're dead, they're no longer transmitting the disease in a community type of sense. I know that sounds very harsh, but it does starts to limit the number of people that are transmitting that disease. So eventually the virus itself is going to flatten its own curve, but what we want to do is we want to flatten it before the virus would do it on its own within a population. Desiree.
I don't know if you remember, I think it was you that was telling us about South Sudan and how they, hello?
Yeah.
Yes, South Sudan, and how they were keeping in contact with the dead bodies, and that's how the spread of Ebola took over
Yes.
these little small villages. So,
Well, that's how it spread so quickly. And what that is that's an example of culture playing a role in disease transmission. So culturally in South Sudan and in other areas, hang on, Wanda, I'll answer your question in a minute. Desiree is talking about an example I gave several months ago, I think, where we were talking about a transmission of disease. And what happened with Ebola is people started to die from Ebola. And in many of those very rural villages, this was a hemorrhagic disease that it's a virus, and it was being spread through parts of central and the mosquito belt area of Africa. And it was moving through very, very small villages. The first place it was discovered was in Zaire. And there was a village in Zaire that someone had contracted Ebola from consuming primate meat. They used to kill monkeys and eat monkeys. And so Ebola originally was transmitted from bats in caves to monkeys. This is what it was traced back to. And then they call that bush meat. And these villagers, they would eat bush meat. They would hunt, and if they killed monkeys, monkeys was considered bush meat. And they would butcher the monkeys and sell the meat and trade it and consume it and that sort of thing. So somewhere along the way, one of these monkeys was infected with Ebola, and the Ebola was transmitted to the butchers that were butchering the bush meat. And they developed this disease. Now, in these small villages, part of the culture when someone dies is you did not mourn their death. Instead, you celebrated their life. And so the people that were dead would be put on large platforms, these kind of like a bed type of thing, and they would put flowers and all kinds of things around them to celebrate who they were. And remember, these are very small villages, maybe 100 people. So everybody knew everyone. And everyone would come out and they would bring this body, and they would literally walk through a village area with the body, and people would come out and they would touch the body and kiss them and tell them goodbye and celebrate them. And it was this, kind of ceremonial type of cultural practice that occurred in many of these villages. They were celebrating the life of this person. They wanted to send them into the afterlife with goodwill and know that their ancestors were looking over them, those sorts of things. And so this was this really important part of their culture. But the problem is Ebola is incredibly contagious. So when they were touching the body and preparing the body for these cultural events, for these rituals, they were then contracting the Ebola themselves, and they would die. And then that ritual would be carried out for that person who died. So this was moving through villages. And eventually what happened in the Zaire Act is the entire village died with the exception of like 2 people. And one of those people left the village and traveled several miles. This was an incredibly remote area. They traveled by foot several miles to, it was I want to say like a rural, what do they call it, Peace Corps type of establishment, and telling them of all of these deaths, that their entire village died in a matter of a few weeks. And they realized that this person was sick as well, and then the World Health Organization was brought in, and it was pretty grim. They went in, and there was an entire village of several people that were dead. So that is an example of a cultural aspect in the transmission of a disease. And of course, everybody in that village got the disease because nobody had any immunity to it. It was a new virus. It had never been seen before. So there was no herd immunity. none at all. And that curve flattened because everybody died. So Ebola is a very deadly disease. It has a very high mortality rate. Now, with supportive treatment in hospitals, we can cure Ebola. Somebody has Ebola, we can give them treatment for it and get them through it. And then once with Ebola, there's reinfection immunity. So the immune system does remember that disease. And now what they have is when someone comes down with Ebola, they're put into a special hospital where people who survived Ebola actually take care of them, because if you're an Ebola survivor, you're immune to the disease. So it was a really interesting study on Ebola and how Ebola spread. But it's just really an example of how culture can play a really big role on transmission of a disease. Let me answer Wanda first. Wanda asked something about, so why do they want to burn the bodies after they die from COVID? Well, because they're concerned, Wanda, remember, viruses are not living. So as long as that virus still has a body to kind of sit inside, the virus could still be viable. So viruses are easily transmitted from dead bodies to the living. If we burn the bodies, then we burn the virus, and it's a way to ensure that basically a body full of virus is not there to infect other people. Jada. Oh, Wanda, I'm so sorry. Was she a COVID? I'm sorry. I'm sorry. My condolences. I know that's hard to
Can you
do.
hear me? Yes, she can hear you. That's my grandson. I'm sorry.
That's okay. Hello, grandson.
Say hi to her.
Hi.
Hello.
So yeah, so I know we've just been going through tough times right now, but
Yeah.
he was telling us that they were supposed to like burn her body after, but I was like, no, don't say that, please, because that doesn't sound right. He was like, I promise you that's what they said to us, and I don't even know if we're gonna have a funeral. So that's why that was my question. If
Yeah. It's done so that they can't, because you can't have a funeral, you can't have open casket, you can't have people, you don't want people in the room with that virus, because the body unfortunately is infected, has a heavy burden, a heavy viral load. So cremation is used to prevent that viral load from being transmitted to anybody that would prepare the body, go to a funeral, family members that might be near the body, anything like that. And so that's why cremation is the choice there. It's for the safety of everyone around them.
Well,
But
he was taking care of her until she was really sick for like 7 days in the hospital because she was taking care of her son, and her son was about he's like 47, I think, or something like that. He weighs about like 300 and something pounds, so he wasn't really that healthy to say, but he was fighting the coronavirus in the house, and so she was taking care of him, and so she got infected by it. So then my cousin, which is my husband's cousin, he feels like he's gonna get infected as well, or that he already is infected because he was taking care of both of them.
are they not testing him?
Well, he doesn't have the symptoms, so they're not testing him. But he's like, but how can I not have the symptoms? You got to test
That's
me.
crazy.
I'm in the house. Like,
Yeah,
so
he needs to be tested.
yeah, he called the ambulance for the first time to take her, and they were like, no, it's better off if she stays here because she's gonna die right there in the emergency room. So they left her there.
This was here in Florida?
No, this was in New York, in the
In New
Bronx.
York. Oh,
Yeah,
that's
and
why.
so he was like, listen, the hospitals are crazy. Don't take
Yeah.
her, please.
Yeah.
She's gonna die right there. They're not even gonna pay attention to her. At least here, if she's, if something happens, she's here at home. You're not gonna be able to see her no more if you take her to the hospital.
Yeah.
No
Yeah.
more. And so that's exactly what he did. She couldn't take it no more. And it got to a point that she was like not, her body was just doing things that like
Yeah.
just doing poop on herself and
Right.
and so when they took her to the hospital, she finally went, and that's it. That was the end. She lasted 7 more days after that. So really, she
Wow.
was with the infection 7 days in the house, no, 14 days in the house, and then 7 days in the hospital.
Yeah.
So she lasted a long time. Like,
Yeah. Yeah.
it's crazy.
Well, I'm very sorry for your family. I'm sorry for your loss. This is a
It's
really
okay.
hard time.
I
So,
know.
yeah.
That's why I wanted to ask if that was true about burning the body.
Yeah, I believe they are trying to do that. I know in New York they've brought in refrigerated trucks and such because
Yeah,
they can't do any of that until someone claims the body.
yeah.
And people are having trouble claiming the bodies because they can't see them, they can't get to them. So they're doing identification virtually, and yeah, there's a whole lot of mess going on up there with the actual bodies themselves.
Oh my
Yeah.
God. Yeah.
Tamara, I'll get to you in a second. Jada, cruise ships considered a cultural aspects. You know, Jada, I don't know if it would be considered a cultural aspect. Is Jada still here? I think she left. I wouldn't necessarily call it cultural, but I would maybe look at it in terms of behavioral, right? People take cruises, and so these cruise ships, they're really tight. There's no social distancing on a cruise ship when you have 1,500 or 3,000 people on a cruise ship. So I wouldn't consider it necessarily cultural in terms of transmission. I would consider it more behavioral. Hey, Tamara. Oh, you didn't have a question. Okay, I just saw you raise your hand. All right, so we're all good with the concept of herd immunity and how that plays a role in protecting people. The idea of herd immunity is to protect those who cannot protect themselves. If the majority of a population is vaccinated or has immunity to a particular disease, then that is going to protect people who can't necessarily get a vaccine. Like maybe infants can't get certain vaccines; they're too young. People who are immunocompromised are not recommended to receive vaccines. The elderly are also limited in some of the vaccines that they can receive. So we need to make sure that we can protect those people when they can't protect themselves. Another concept in herd immunity is the idea of cocooning. In cocooning, if someone has like a newborn, this first came up with preemies. When somebody has a preemie, premature newborns cannot receive vaccines like a normal term newborn can. They're not fully developed yet, and they have to develop usually in a hospital setting, and in a very protected setting. So when a set of parents have a preemie, they have a premature infant, oftentimes people in the household or people that are going to be in contact with the baby are asked to get a set of booster vaccines to just give that extra layer of protection to make sure that they don't possibly bring a disease into the newborn itself, because preemies have absolutely no physical defenses against diseases, and so they have to be really highly protected. And so that cocooning, kind of wrapping the baby up in this vaccine cocoon, helps to prevent the spread of that disease to premature and underdeveloped newborns. So the idea of the anti-vaccine movement has really weakened herd immunity in the United States. It's also done this in Europe and other parts of the world as well. And diseases that we thought were fairly eradicated or were very rare are now making a pretty big comeback. A 12% increase in a disease that was once considered almost eradicated or very rare is a really big increase. That's a lot of people. Think about it. If we have 30 million people or 65 million people in the United States, 12% of 65 million is pretty big, right? So we're looking at over 6 million people. That's a big jump in disease in a population. I just want to make a comment. I am a big vaccine advocate. That's just a personal opinion. Everyone can make their own opinion, but what we are going through right now is what happens when no one's vaccinated. So we don't have a vaccine right now. It's definitely not by choice, but this is what happens with diseases. So when measles ran through the United States, this is kind of what it was like, although we didn't have the same type of quarantining going on that we do now. Same thing with polio and that kind of thing. Wanda, that is a personal decision. Like I said, I get the flu vaccine every year and make my son get it. You don't. That's perfectly fine. It's your decision not to do that. Do you get the other vaccines, the MMR and those sorts of things? Why are you scared of it? How many people die of the flu, and how many people die of the flu vaccine? Yes, Victoria.
How do they figure out like when to give these vaccines? Like at what age did they determine this vaccine at this time versus this one at this time?
Well, that's part of the 10-year research that goes into getting a vaccine approved. So a lot of times they'll test the vaccines first in like mammals. There's levels of testing that go on with the vaccine. So they first test vaccines in mammals like mice or in tissue samples, like cell cultures, to ensure the vaccine is effective as well as doesn't have any side effects. Then once it's shown effective and safe in, say, mice, they then move on to primates. So they would look at like the rhesus monkeys and such. They would look at efficiency in those organisms. And then eventually it goes to human trials. So many vaccines, they don't test in infants, so they don't recommend them for infants. It's not that they tested it in infants and there were side effects, it's that they did not test them below a certain age group, so they're not going to give them. That's kind of an ethical decision in terms of vaccines. So if we didn't test the flu vaccine against in 5-year-olds, they're not going to give it to 5-year-olds. So they just show that that the vaccine has good efficiency and that there are very few side effects. And it takes anywhere from about 6 to 10 years for a vaccine to pass through all of those tests. In terms of the actual tests that they do and experiments they do to ensure that kind of efficiency, I would have to, I don't know that offhand. I just know it's a long process, and if they do not test in specific age groups, they're not going to recommend or require a vaccine for that age group. Does that make sense, Victoria? The COVID vaccine, well, one, they're going to be surpassing a whole lot of FDA approval blockades. They're going to streamline it. They're going to move it through quickly. The other thing to remember is they're basing the COVID vaccine off of prior research that was done on SARS. The same reason that they could get the H1N1 vaccine out in about 6-8 months is because it was a flu vaccine. And so we already had the premise in testing for flu vaccine in previous, because of all of the flu vaccines that are used. So because COVID is so closely related to SARS, there was a whole lot of research done on SARS vaccine that's being applied to the idea of developing a COVID vaccine. But they're still looking at, they're saying 18 months. I don't see it happening that quickly, but they may come out with one that's short-term immunity while they're trying to develop one that has greater long-term immunity. So Wanda, you're going to get the COVID vaccine? No. And Victoria, can I ask why you would pass on the COVID vaccine?
I personally feel like we've been researching the other closely related diseases, SARS, and I feel like they don't have a vaccine for these diseases for a reason yet, and I feel like they're rushing it, and by bypassing all these FDA rings or loops, it's gonna put some people in a really bad position, and I'll get it, but I want the research to back it first.
Yeah, I kind of agree with you. I was that way with the chickenpox vaccine. I was not crazy about the idea of a chickenpox vaccine for my son. It was too late for me. I had chickenpox as a child, and to me, chickenpox is not a deadly disease in a child, and I know that they're going to have greater immunity by getting it than from a vaccine. So when I spoke with my doctor about it, I said, I really don't want to do this. I'd rather he has greater immunity. And then I remembered about shingles, and I thought, well, I don't want him to have to suffer shingles later on in life. So yes, it was very etchy, Wanda, I agree. But now my son is vaccinated. He not only doesn't get chickenpox, but he will not develop shingles later in life. And that was the bigger one for me, because shingles is a much more painful disease. So the idea of vaccinate or not vaccinate is a really personal one. But what I really want you guys to kind of take away from that argument is do the research. I agree with Victoria in that they are really kind of pushing this COVID vaccine very quickly. Now, we are really, really good at developing vaccines, particularly here in the United States. We have tons of research. We have really great researchers that do it, and the companies are very thorough in it. However, and I do know there's a whole lot of research that was done on SARS. Now, the SARS vaccine was kind of dropped off the radar because SARS kind of went away, and there was really not a lot of concern in SARS popping up again, and to push forward that whole idea of developing a SARS vaccine. Wanda, you have another question?
Yeah, Trump said that he was going to take the COVID injection even if he doesn't have the virus.
He's going to take the vaccine?
Yeah, he said, that's what he said, that he was going to take the vaccine even though he doesn't have the virus, just so people could trust it.
He does realize that the whole point of taking the vaccine is because you didn't have the virus, right?
Yeah, so people like, really, you're going to take the vaccine? Yeah, that's what I was going to tell you. So let's see what happens.
Okay, then we will let him be the guinea pig.
He'll be the guinea pig.
What do you think, Victoria? We'll let President Trump be the guinea pig on the COVID vaccine?
Look, all I know is he could say whatever he wants. Ultimately, whether or not he gets that vaccine is still HIPAA protected, so he can say it all he wants. Doesn't mean he's necessarily going to take it. And for one, I will be doing my own research before I take any vaccine that's coming out in 18 months. It's just
there you go, Victoria. That's it.
We will know when he gets sick on it. So
that's right. Tamara, he has it? You think he has it, Tamara? You think he has COVID? Is that what you're saying?
Yes, I think he has it.
That's why he wants to take the injection. That's what everybody thinks.
That, or he's tricking people so that they can feel safe and they will take it, and then he's going to see how that works out.
I don't know. As bold and honest as he is, he probably will take the COVID just to prove a point. And
oh my goodness, you guys are such conspiracy theorists. All right, I'm not talking politics.
We are in injection, and it's going to be water.
We are in micro. I am not talking politics, so let's leave Trump out of it. All right. So let's talk about the compromise. Let's see, Jalen. Why do you believe COVID will become endemic in a population like the flu? Jalen, that's a great question. You know what? It's in the population. Try to get it out. Think about that. How do we get rid of it? It's here. It's infecting people. So it will eventually become endemic, kind of like the flu. But with vaccines and herd immunity and such, it will not be the pandemic that we are seeing now. Remember, we're seeing this type of infection and these number of deaths because nobody has immunity. There's no naturally acquired immunity. There's no vaccine acquired immunity or passive immunity. Nobody has immunity to this. It's never been seen before in the human population. So it has a really high R0 value, which is its transmissibility value. It has a fairly decent mortality rate. It does kill people about between 2 to 3% here in the United States. Other countries that, when their health system got overrun, take Italy, for example. Italy had over a 10% mortality rate, and because they had patients who were untreated. They could not treat every patient that was coming in. So there is no existing immunity to this disease, and that's why people are so susceptible to it. If we had some kind of herd immunity, then we would see this disease slow down in its spread. We wouldn't have this type of quarantining that we've got going on. We probably also would not have the same mortality rate because people would have some immunity to it. Eventually, people will develop it and we're going to get herd immunity, but there's always going to be a fragment of the population that will not develop immunity to it. And either through anti-vaccine movement or through pre-existing disease, or they're immunocompromised, whatever the case may be, or it could be socioeconomic. Maybe they can't afford the vaccines. So those are all factors in determining whether we can develop herd immunity here in the United States. When I was younger and they did vaccines were free. You went to the health clinic, to the health department, and vaccines did not cost anything. You did not pay for them. And that was to ensure that school-aged children going into school would receive vaccines against childhood diseases, so that they still are in the health department. That's good, Victoria. So that in school settings where kids are close together and in closed rooms and those sorts of things, that these children are not spreading disease to each other. Okay, so the concept of herd immunity, yeah, and clinics do them pretty inexpensively too as well, yeah. But there are still some, like Gardasil for young girls and for young men is one that's not part of the vaccine schedule. It's a recommended but not required, at least as far as I understand it. So some vaccines are still kind of expensive in addition to those like standard vaccine schedule. Yeah, that one's super expensive. You have to have insurance for that one, which is unfair. So that's a whole equity issue. Yeah, that's a whole equity issue that I don't want to get into right at this moment. Oh, Wanda, you make me laugh. Okay, Wanda, that's fine. You don't have to do it. It's not a requirement. That's why we live in the United States, right? We all have our own freedoms to make those choices. Okay, so herd immunity. The concept, again, of herd immunity is to protect those who can't protect themselves. And what I wanted to show you here is here in the United States, we have from up here 1950. In 1950, there was an epidemic or an outbreak of measles among children in particular. And we were reaching upwards about 800,000, nearly 1 million cases. Now, this is in 1950. I don't know what the population of the U.S. was in 1950, but it was much less than it is now. So 800,000, nearly 1 million people in what we have here, like 1956, a big outbreak of it here. In this case, nearly 1 million people, that's a large number of people in a smaller population. And then, of course, it's just like any other epidemic curve. It peaked, right? It peaked up here near just around 800,000, just below 800,000 people. And then, of course, our curve comes back down. But then we saw a little bit later, a year or so later, we start seeing little epidemics here and there. Now, this is before a vaccine was licensed and issued. So a vaccine had not been developed yet. So any herd immunity that would have occurred in this time frame over here would have been naturally acquired. And you can see this is what they mean by flattening the curve, right? So they start quarantining and stuff, and these curves here are what they're talking about. All those right there. So I'm going to delete that so it's not so messy. And again, this time period here, we had no vaccine. So we had a pretty high number of cases, upwards of almost 800,000. And then we introduced a vaccine here in 1962. 1962, vaccines get issued, and look what happens to the curve. It goes to less than 100,000. We're talking maybe 10,000. But we were still seeing little peaks here, so they recommended a booster. So you got the first vaccine, and then a few years later, you receive a booster vaccine. We get the booster vaccine, we are at near zero. Then, in early 2000, right around here, and into 2003 is when the anti-vaccine movement started to really hit here in the United States. And all of a sudden, we start seeing our curve come back up. And we start seeing increases because we have fewer children vaccinated against the disease. And if you are vaccinated, doesn't mean that you aren't exposed. You're still exposed, just that your immune system gets rid of it before you can get sick. Okay? So for a very short period of time, maybe a few days, you could transmit that disease. You possibly could, but almost everybody else is vaccinated against it. So the disease is moving around from person to person, but it can't infect anyone because everyone's vaccinated. Well, if we start reducing the number of vaccinated people, then we have people who are now susceptible to it. And it will be transmitted to them, and they will then harbor the disease. And this is why the disease becomes endemic in a population, because we are always going to have a percentage of population that does not have immunity to it. And so they become reservoirs of that disease. If I'm exposed to measles, it may be in my system for a day or two, only a couple of viruses, but my immune system destroys it before those viruses can ever gain entry into my cells and begin replicating. The odds of me transmitting it during that time is incredibly low, but it doesn't mean that I can't. But everyone around me is vaccinated, and so they're going to be in the same boat. But if someone is not vaccinated, they don't have immunity to it, then that disease can harbor in that person, and they become what's regarded as a reservoir of disease. So here we see in measles in England from 1996 to 2010, this is during that anti-vaccine movement. So in the mid-90s, the anti-vaccine movement really that's when Andrew Wakefield was starting to introduce his concepts. And so children were not getting vaccinated around this time. And for a while, it really didn't make much difference. You can see these numbers are still pretty low, 200, right? Confirmed cases, 200 in an entire country is pretty low. But in around 2001, those kids that were born in 1996 and 1997 who never received vaccines, what do? They go to school. So now they enter into preschool and kindergarten, and now we start to see the cases go up. We have a natural drop in the curve, and then in 2005, what happens? These kids now go to bigger schools. They go to grade school. And when they go into grade school, we see a huge spike in the number of cases because we have fewer kids with immunity, and then we have, of course, the spreading of this disease, and we're putting them in a room with a whole bunch of other kids, very close contact, and so the disease spreads very easily, particularly in a school-type setting. Yes, if an adult gets chickenpox, it can be deadly for adults, Wanda. The younger you are when you get chickenpox, the more mild the disease will be. Okay, severity. So a disease that is an acute disease, symptoms will develop very rapidly. That's kind of what we're seeing with COVID, unless you're asymptomatic. But let's say somebody is symptomatic, the disease hits an acute stage very quickly, within a matter of a couple of days, 7 days, 10 days. That's pretty quick. A chronic disease is one that develops very slowly. And then, of course, a subacute disease is where it's kind of in between. The person will develop an acute stage, so they'll have a viral load up here. And then instead of going all the way back down, they just kind of mess around here in the middle. An example of a subacute disease would be like mono, right? Mononucleosis. And then a latent disease is one where we have a long period of time with no symptoms. The person is asymptomatic, and then the disease will return. Isabella, I wish I knew why some people were asymptomatic. I have no idea. I can't answer that question. I just don't. Some people may have better immune systems. They may have a lower viral load. No idea. Doesn't affect them the same way that it does others. Okay, so how involved is the host in disease in a population? So if we have what's called a local infection, this is where the pathogens are kind of regulated to a small area. Think like an infected cut. So you have a paper cut, it gets infected, and so you don't, that's a local infection. A systemic infection is one that occurs throughout the body, usually in the circulatory system. And this is some examples of that would be septicemia, or which is a form of systemic infection. Another one that occurs is viral infections. COVID is actually a systemic infection. Just prior to death, the patient usually has a multi-organ shutdown. One of the problems with COVID is its glycoproteins are matching to a receptor that's found on multiple tissue types. So it can actually enter into liver tissue, kidneys, that sort of thing. So it is actually more than just respiratory. Yes, Desreen?
So, like how you said, each virus has like its specific spot that it wants to be in the body, where it's most, I guess, the most nutrients is found, or like environment specific. So the virus, you said, they said no eyes and nose, like the mucosa membrane. So now you're saying that this virus also has the compatibility to be susceptible to like liver cells and stuff like that.
Yeah, what they're finding is that the glycoprotein is complementary to receptors found in other tissue types. The mucous membranes, eyes, nose, that sort of thing, that's called a portal of entry. and that is how the virus gets into the body. It most strongly affects its target is respiratory tissue. So it gets into the lungs and causes, because it's kind of, the lungs are a weak spot. That's a huge, big, giant, huge mucous membrane. And you inhale this virus, and that's what the virus comes into contact with first. It gets into the mucous membranes and it gets into the lungs, and so it infects those cells first. What I'm talking about is very late stage. So if somebody is infected and they're incredibly ill, they go into the hospital, what they're finding is this virus does have the ability to bind to receptors on other tissue types, but you're not going to get a COVID liver infection. You're going to get a COVID respiratory infection. And then right before death is when they're starting to see multi-organ failure. And that's because the patient has a gigantic viral load. It's really big. And eventually it can start moving into, because of cellular damage and other factors in the lungs, that virus now starts moving into the bloodstream and can move throughout the body. And if it spikes are complementary to receptors on other cells of other tissue types, then that virus will be able to gain entry into those cells. Okay. But that is very, very late stage. So you're not going to, if you contract the COVID virus, you're not going to contract the COVID virus and get liver failure. You're going to contract the COVID virus and you're going to get a respiratory infection.
Do you enter into that cytotoxic storm stage where, like?
I believe so, and that's part of that. The cytokine storm thing is part of the, that cytokine storm is kind of that when the person goes into either respiratory arrest or a shock. They go into shock. I don't know enough about the end stage. I don't treat patients. I'm not a medical doctor, so I don't have a lot of resources on what's happening at the end of this infection stage for people who are dying from it. I haven't found a lot of research and a lot of reports on that yet. I don't think they really have it. They're still doing biopsies and autopsies, and they're still trying to figure out even the pathogenicity of this virus. What is it doing? There's a whole lot that's unknown about this particular virus yet. So I don't want to say to you, oh, it's going to infect cells. I just want to
No. It's just like, it was
I don't want to misinform anyone. I just want you to understand that I'm looking at it from a scientific standpoint. What does this virus do once it's in the body? And so those are just the things
because I don't understand why we have things like Klebsiella pneumonia, which has a hard capsule and can't be taken out of the lungs and only stays in the lungs. And then you have certain other viruses that choose whether they want to go in the lungs or infect somewhere else. It's like, I feel like we're so under advanced. These viruses have so many things up their sleeves to be in different places.
Let me give you an example. So here are some cells, right? Here are some cells. Oh, wait, I want to make it different. Now, this cell here so these are different cell types. We'll label them for a second. So this is a kidney cell. This is a liver cell, and this is a mucosal membrane cell, right? An endothelial cell of a mucosal membrane. If I'm a virus, so I'm gonna make myself a little, that's a really bad virus. If I'm a virus and I want to enter into a kidney cell, then my spike is gonna be round it's gonna be, I'm going to create a viral spike that's square, because this square is going to match my kidney cell receptor. These are the receptors on my kidney cell. Let me make that square. My drawing is really bad, guys.
No, it's great. I see.
So my virus here can now enter into a kidney cell, but this virus can't enter into a liver cell because a liver cell requires a round one. This guy could. right? This guy over here could enter into a liver cell, but he can't enter into a kidney cell because kidney cells their receptors only take a square glycoprotein spike on a virus, whereas this virus over here has a round one. Well, that one can infect a liver cell. And if I have another virus over here that has a triangular one, right, like a diamond-shaped one, like that, then it can bind over here. And it can enter into the mucosal membranes. So what happens with some viruses is some viruses are very, very strictly regulated to what cells they can inhabit. Maybe liver cells are the only cells in the body that express this round type of receptor. So that's the only cell type that this virus right here would be able to enter. But if I have cells that share receptors, and say my mucosal membrane has a round receptor as well as a square receptor, then all three of my viruses have the ability to enter into a mucosal cell. But they don't have the ability to enter into the others because they don't have those receptors. So what's happening with COVID is you have a COVID virus that has a single glycoprotein on it that, say, is round like that. Well, alveoli and the mucosal membrane cells have lots of receptors that are that enable for that round glycoprotein to attach to it and gain entry into the cell. But the problem is that the receptor that glycoprotein is complementary for is sometimes also found on other cells. And so other cells use that receptor for a purpose that all cells would need it for, and COVID is taking advantage of it by binding to that particular receptor. Let me look up real quick. They did discover the receptor. So it's called the ACE2 is the name of the receptor. Let me see if they have a video on here. I'm going to share, thanks, get rid of that. And I'm going to share a page with you guys. I know time is up, but I'll just share this with you real quick. Okay, so in looking for drugs to try and inhibit the infection, so they're looking for a way to try and treat this so that they can block. Here's the COVID. Here's the COVID virus, and they want to block all of these glycoprotein receptors. That's what all these little spikes are. So these are called glycoproteins, and they're viral spikes. These spikes are what will bind to a receptor in the cell to allow that virus to gain entry into the cell. So what they've discovered is that COVID-19 binds to a receptor known as the ACE2 receptor. And the protein, the glycoprotein spike on it is called the S protein. During infection, the protein, all right, on the actual virus, it gets cleaved, meaning it gets cut into subunits 1 and 2. 1 contains the domain that actually binds to the cell receptor itself. S2 then enhances and creates membrane fusion. So remember back in our virus chapter, we talked about how viruses gain entry into cells. Well, the COVID gains entry into cells that have an ACE2 receptor by membrane fusion. So this little receptor on here, I think you guys can see my mouse, these little glycoprotein, these S spikes, will bind to a receptor on the surface. They'll bind to what's known as an ACE2 receptor. They'll bind to that receptor and then fuse their membrane with the cell membrane and drop the capsid inside of the cell. So they now have used what's called cryogenic electron microscopy to look at the structure of the ACE2 receptor, and that's what they're looking at here. So this is a picture of the membrane of virus, right? So in gray here is our phospholipid bilayer, and then they have this three-dimensional structure of that protein. We can actually, we're supposed to be able to mess with that, but I can't get it to work right now. And then they looked at the structures that could only bind if the virus interacts with a region of that protein. This is all crazy stuff, but this is the ACE2 right here. I can't write on this, but this is the ACE2 receptor here. I'm supposed to be able to move that, but it won't let me. So what they also looked at is SARS. So SARS also uses that ACE2 receptor. And so they're looking to target the receptor to prevent the viral spikes from being able to bind to it. So Isabella, you asked why some people might be asymptomatic. Maybe, just maybe, their ACE2 receptor, they have a viral load, the virus is in their system, but that ACE2 receptor is not as receptive to the glycoprotein, to that S protein on the COVID virus than it is for other people. So there's a few factors in disease. One is a viral load. How much virus did the person get exposed to begin with? Was it a whole lot of virus, so it all gets into the system very quickly in a very high concentration, which would logically make sense that the person would have a more severe form of the disease? Or did that person get exposed to a low level of viruses and it's taking a longer time for those viruses to replicate inside of their cells for them to get a viral load that's high enough for them to start showing symptoms? And if they don't get a really strong, heavy dose of the virus, then their immune system could possibly knock down that virus and make it a very mild or asymptomatic form of the disease before that virus has a chance to really take over. So many times, whether some people are asymptomatic or have a mild, moderate, or severe form of the disease, right now is believed to, a big part of that is how much of the virus were you originally exposed to. For example, in Victoria, I do not wish this on you at all, but Victoria is in a healthcare setting. So Victoria and Josu both are in a setting where they are exposed to a really high concentration of those viruses, a high number of viruses. So for them, bye Wanda, so for them, that exposure is much higher. And if they were to be exposed to those high numbers, they could possibly have a more severe form of the disease than maybe if I went to the grocery store and bumped into somebody and got a low viral load. My form of the disease might be a little more either asymptomatic or very, very mild to where I don't even know that I have it. Does that help? I think someone asked that question, Isabella. Okay, great. So of course we went off on another COVID tangent today, but it's just so relevant, and there's so much being learned about it right now. So I do think it's just a more important conversation than going through terminology in epidemiology. So what we're going to do is next week when we meet Monday, we're going to finish this up. I was hoping to finish it today, but I of course got squirreled. We'll finish this up on Monday, and we're going to talk about that R0 value. It's called, I'll type it in here. It's called an R-N-O-U-G-H-T, R0. R0 is a numerical. It's a number value, a mathematical value that's given to how transmissible a disease is, and the R0 number results in the number of people, if somebody is infected with a virus, how many other people they would possibly infect. So I found an article on this, and I'm going to get some screenshots of it that compares the R0 value of COVID to other diseases in the past. And we'll take a look at that in transmission. Oh, Adanya, the case study. I have to email it to you. Remember, guys, there are two different case studies. There's the one that I'm going to email to you that you will solve that case study and take care of it. And then the second one is the one you do in the discussion board that you write your own. So you're going to write a case study and then solve someone else's. That one's a kind of pretty simple one. I will send the case studies this week, Adanya. I will email them to you. I just am a little behind in getting them out. I need to adjust a couple of them. So you'll get an email in D2L with your case study attached to it. Okay, great. Does anybody have any other questions? Anything they want to talk about or add? Yes, Desiree.
Okay, just real quick before I go. We're
Sure.
having lab today again. Yes.
We have lab today if you need help with anything. So what I've been doing is our first meeting of the week is when I go over everything that we're doing. And then on Wednesday or Thursday, whenever your lab is, you can come in. I will be there and you can ask questions. We can go through stuff. I can help you with anything you need help with. So if you don't have any questions or anything, you're good. You don't have to come today.
Okay, all right then. One more question. So the case
Sure.
study for this one here is that there was a date. It says December. I know that's not the day.
Oh, no, I got to fix the dates. I'll fix it.
But it's not anytime soon. So I mean,
No,
I don't have to
it's
worry
not for
about
like,
it.
no, don't worry about it right now. I'll fix it. Let me put it on my list for today. Case study dates.
And the antibiotic lecture, I still can't see it. It says it was removed.
Okay, I'll have to find it and re-establish it.
Okay, thank you so
So
much.
it must be a broken link. So
Okay.
antibiotic lecture. Okay, will do. Thank you, Desiree, for letting me know.
Have a good day.
All right, guys, have a great day. And let me know if you need anything. Hi, Svetlana. How are you? I didn't get to say hi to you before. And Stephanie. Bye, Michelle. Oh, Josu, you have a question about the lab practice quiz? You too, Michelle.
Yes, I download the lab practice quiz, but I don't wanna open it up so you don't send me to the real quiz.
You
That's what I was
downloaded
asking.
the quiz? How do you download the quiz?
No, not the quiz, the lockdown, the
Oh, the
lockdown.
lockdown browser.
Yeah, I downloaded it
That's,
on my desktop,
uh-huh. Okay,
but I don't wanna open it up yet because we have the test till the 11th, right?
correct. The
Yeah.
lockdown browser will only kick in for exam 3, the written exam. For your quiz, your weekly
Yeah.
quiz, I don't require the lockdown browser for that.
No, for the exam I was talking
But
about.
for the exam, yes. So once you open the exam, you have to finish it.
Okay, that's why I downloaded it on my desktop, but I didn't open
Yeah. So take the exam on your desktop, because if you don't have the lockdown browser, it won't let you open the exam.
it. Okay, thank you.
Yeah, so since you have that on your desktop at home, do it at home on your desktop.
Okay, thank you.
You're welcome. You're welcome. Anybody else? Natalie, how are you doing? Oh, Natalie left. All right, Stephanie, are you going to come to lab? You too, Josu. Take care of yourself, okay? Stay safe. Stephanie, I know you wanted to meet to go over your exam. Are you coming to lab today? Okay. All right. Well, Stephanie, I'll be in the lab. So if you want to come by the lab or text me, and we'll come up with a time to go over your exam later today. So I will see everybody at 1 o'clock.